Hi, good afternoon. Thank you very much for being here. My name is Nancy Zurita, and this poster is about the development of polymeric polymethyl methacrylate scaffolds with nano-silver, zirconia, bioactive glass, and this is for the enhancement of osseous repair. As a brief introduction, it is important to remind that bone is a highly dynamic and integrating tissue capable of remodeling itself throughout life. One of the materials that present attractive characteristics as bone substitute are bioglasses, due to their capability to form crystalline hydroxyapatite on the surface, which posteriorly bonds with the surrounding tissue and release ions that activate expression of osteogenic genes. Nevertheless, bioactive glasses are limited in their uses by their low mechanical resistance and crack propagation. It has been found that the use of zirconia in certain amounts subserves the increment of toughness in bioglasses, and in an interesting way, it enhances the biological response, triggering an intracellular signaling, which leads to cell adhesion and proliferation. As known, zirconia devices are widely used for bone and dental reconstruction. Another complication to avoid in osseous repairment are infections. It is known that bacterial infection can lead to tissue necrosis, and at this time, some antibiotics have poor efficacy against bacteria embedded in biofilms. That is why silver nanoparticles have several applications in biomedical areas due to their excellent broad-spectrum antibacterial activity, including protection against drug-resistant bacteria. In this project, the salt gel synthesis for the obtainment of the Nano-Silver Zirconia-Doped bioglass was carried out taking advantages of its easiness and economic feasibility, as we can observe in figure 1. As we can see, the polymeric salt gel method is based on hydrolysis of tetraethyl orthosilicate and condensation of a mixture of metal salts. It is performed at room temperature and offers the control over stoichiometry and structural homogeneity. In figure 2, we observe the polymerization of methyl methacrylate employing benzoyl peroxide as a free radical initiator. The reaction was performed at 80 Celsius degrees for 7 hours under vigorous stirring. The preparation of the 3D scaffolds was done by first dissolving the polymethyl methacrylate into acetone, and the bioceramic silver zirconia bioglass particles were then added. The designed compositions of bioceramic polymethyl methacrylate hybrid scaffolds were 1 at 30% of bioceramic, 70% of the polymeric phase. Here, we named these scaffolds as 3D SC1. And the second proportion was of 70% of bioceramic, 30% of the polymeric phase, named as 3D SC2. The porosity of the scaffolds was obtained by applying the solvent casting and particle leaching method. For that, sodium chloride particles with a maximum diameter of 500 micrometers were incorporated into the mixture, and posteriorly, it was pressed into Teflon molds until the complete evaporation of the solvent. The obtained scaffolds were then dismounted and immerse it into the ionized water by 2 hours to eliminate the salt, and then they were dried in an oven. The X-ray refraction and the Fourier transform infrared analysis of the bioceramic nano-silver zirconia-doped bioactive glass demonstrated the evidence of the glassy ceramic nature of the hybrid nanoparticles, as figure 4 and 5 show. The morphologies of the nano-silver zirconia-doped bioactive glass, the polymethyl methacrylate, and the scaffolds in their two proportions are shown in figures 6 and 7. Figure 6a represents the nanoparticles of the hybrid bioactive glass. The particles present a homogeneous morphology and a structure, but due to the particle size that are at nanoscale, they form agglomerates as a consequence of the van der Waals forces. Figure 6b reveals the average particle size of the polymethyl methacrylate powder, which is approximately 40 micrometers in a spherical shape. Figure 7a shows the morphology of the first proportion of the scaffolds, the 3D-SC1, that, if we remember, it's 30-70. As expected, the morphology is more similar to the polymeric phase due to the major amount of this polymeric component. In figure 7b, the morphology is heterogeneous. The proportion here is at 70% of the bioceramic part, 30% of the polymeric part. So it is possible to observe that this is very heterogeneous, and also that the polymeric phase is present in strands. The conclusions of this project are mainly that, well, at first we are developing bioglass scaffolds, but with improved interfacial properties and antibacterial characteristics. Along, we expect that these scaffolds present adequate mechanical strength, corrosion resistance, and of course, high biocompatibility. At this moment, mechanical compression properties of the scaffolds are being evaluated by dynamic compression to determine the impact of the dopants in the bioglassy materials. At last, I want to thank to CONACYT for all the support, to my research group at the Mechanical Engineering Faculty, and of course, to all of you for being listening to this explication. Have an excellent week, and we're looking forward. Goodbye.